Okay, so maybe we should slowly get going. So, so it's a great pleasure to have our Atlas colleagues here who will tell us about this exciting new development. In fact, a new development, a new repackaging of the old development. Which actually for statistical analysis, which may actually suit perfectly our needs, because what we are doing is essentially fairly similar, and as far as I can tell, almost everything we need other than sort of the window dressing is already there. So and we can sort of discuss at the end or sort of you know, what kind of other, you know, little plots we need. But I think in terms of the machinery, I think everything seems to be in place. So who's giving the talk? Lukas, Matthew?
Yeah, I'm
okay.
giving the talk.
All right, so Lukas, why don't you get started?
Okay, yeah, so let me also say thanks for inviting us. So maybe it's one of the times where we can kind of collaborate nicely across different LHC experiments. So yeah, I just wanted to give like a short overview over pyhf. As you said, it's a little bit of a repackaging or reimagination of something that we've been using for quite some time. And so basically, kind of as a sorry. Yeah, so it's a kind of broad categorization. So broadly, kind of at the LHC, we're typically doing two types of statistical analyses. So either we do binned analyses or unbinned analyses. And so in Atlas, and I'm sure in CMS as well, a lot of the analysis that we're doing end up being binned analysis, while, for example, LHCb is doing a lot of unbinned analyses. And so over the years, we've kind of developed a lot of tooling around doing these binned analysis in a kind of nice way. And so in Atlas, basically the way that we do binned analysis is that we use a tool called HistFactory. And so this is basically a way for us to build binned likelihoods with predefined building blocks for systematics and, you know, data-driven estimates and all that stuff. And it's really quite widely used in Atlas. So we use it both for for standard model analyses, SUSY analysis. Almost all SUSY results are basically built with this. Exotics, which I guess is the equivalent of B2G in Atlas, is using this quite broadly as well. And so it's been quite successful. And I think kind of broadly, it's similar to what you've been doing with Combine. And so basically, so the building blocks that we have here is kind of summarized in this formula, which I'll not go through in detail, but essentially the way that the PDF is built is kind of designed as a joint measurement of multiple phase space regions, or something that we call channels. And then in each channel, you kind of build up kind of your expectation value, which is then your expected number of events that you stick into your Poisson, as kind of the sum of multiple processes, or what we call samples. And so those can be either simulation based, or it can be data driven, and they all kind of add up to the overall expected number of events. And then, but each sample is then can be parameterized in order to model systematics. So if you're unsure exactly what the, you know, normalization is, you know, you can add a modifier to reflect that parameterization, or you have, you know, some kind of systematics where you have like an up or down variation. You can interpolate vertically between these in a smooth, like parameterized manner, or so you can have all these types of things, or like, you know, shape systematics. And so generally there are two classes of these modifiers. They're constraint modifiers that kind of implement systematics, and they're paired with a constraint term, which is shown in red in the formula above. Or you can have unconstrained modifiers that just scale the expected number of events, and those are typically used for things like signal strength, or cross sections that you want to measure in situ or something like that. Okay, so the original implementation of this type of PDF template has been in root, but of course it's completely defined in terms of like mathematical building blocks. That doesn't really need to be in root. And so basically one thing we kind of investigated then is to replace or rewrite that in kind of modern kind of Pythonic machine learning tools. Okay, so the classic kind of way that we structure statistical analysis in Atlas is usually kind of we do like a division of labor of sorts. So like historically it's been, okay, we use root for all the basic computations, and then there's like root fit and root stats as a kind of statistics foundation. And then on top of that, you have this PDF template of HistFactory, which uses basically the tools of root fit in order to build up the formula that I showed in the previous slide. And then on top of this PDF template, we usually have like statistics frameworks, and there are multiple frameworks that all use HistFactory when they try to kind of give like the full user experience, or as you said, window dressing that kind of provides you the tools to do like all the important diagnostics, like pull plots, impact plots, and, you know, pre-fit, post-fit plots, and all these types of things. And so basically what we've kind of looked at is, because HistFactory is kind of independent in its definitions from root, we've basically tried to replace kind of the main foundation in order to gain some performance. And so then HistFactory basically becomes this Python version of HistFactory. That's why it's called pyhf. And then it's built on top of like standard Python and machine learning tools. Okay, so the reason why we thought it's interesting, it's not because we're kind of fundamentally against root, but because we kind of saw early on that we could get a lot of kind of speed ups out of this. And so here we kind of see some kind of computation. So on the top row, there are like two example likelihoods where we were kind of comparing kind of the performance in computing, let's say the test statistic 200 times in root, and let's say in pyhf. And so I'll go into this point later that we have like multiple ways to run pyhf. So, but basically like the first line is root benchmark, and then the bottom three are basically what we can do with pyhf. And then you can see you can get a pretty dramatic speed up of like a factor of a couple of hundred. And so that's nice. What's also nice is that the workspace itself becomes a little bit more compact. And so you can get like a order of magnitude space savings there. And so overall, it's been nice to see that we can get this much performance out of it. And as we are kind of looking forward to run 3 and run 4, where, you know, our statistical analysis will become more complicated, you know, having this type of performance increase is certainly nice to have. Okay, so the kind of UI improvements. So we kind of have like a command line interface that does allow you to do like basic stuff. And my understanding is that Combine kind of operates on a similar level, where a lot of stuff kind of goes through the command line. And then we have a Python API that kind of gives you more detailed access to all the things. And so in its most vanilla form, kind of you can use pyhf with the pure scientific Python stack without any like you know, complicated dependencies. So you only need NumPy and SciPy, but then you can have optional extensions, and so it doesn't require you to use root. So a lot of analyses by now in Atlas, you know, in the later stages, they try to do like a pure Python workflow. And so if so oftentimes like the only point where they need root is for statistics. And so that's certainly nice to have if you like if you don't need root anywhere else in your workflow. Okay, so one nice side effect of this effort, so of course we have like all the UI and like performance gains, but a nice side effect has been that we're able, through this kind of reassessment of HistFactory, we're able to kind of make a significant step in like the open data and kind of knowledge or results dissemination area in terms of kind of publishing the likelihood. So this has been discussed for many years in the context of the LHC, that, you know, the likelihood is like the central object that holds all of the information on the measurement, like all the correlations between the different you know, measurements that you're doing inside of your big likelihood, and all the different systematics that you have modeled, and all of these details kind of are important for kind of posterity. And so it's been kind of recognized for a long time that it would be good to publish the likelihoods and the statistical models as a kind of very high information data product. But we weren't able to get there in an easy way. And so like through this pyhf development, we've been able to kind of get Atlas to publish these full likelihoods. So CMS has been doing these simplified likelihoods for quite some time, and that kind of served, of course, also a bit as an inspiration. But like in contrast to that, kind of here we have like the full shebang, right? So we have the full like list of systematics and correlations and all these things. And so I think that was a significant step that we were able to kind of push Atlas to do. Okay, so kind of here's just like a kind of format or like the main part that kind of changed in terms of the original HistFactory and the kind of pyhf version. So in the original HistFactory, the way that kind of we organized our workspaces, or kind of we collected all the information that were used to generate the workspaces, has been a bunch of XML files that are interlinked between each other. And then inside of those XML files, you reference root files, and in those root files, you have like all the different templates that are being used in terms of building the workspace. And so that's basically unchanged. The only thing that we changed is instead of having all these multiple files that need to be kind of in a certain directory structure and the root files, which kind of tie you to the root data format, we kind of developed a JSON file format where all of the data is inline. So the entire workspace is a single JSON file, and that's kind of what enabled this likelihood preservation in an easy way, because your entire likelihood is one kind of easy to read, like by machines and human JSON file that you can then kind of put on HEP data in an easy way. And it's not necessarily linked to a very specific technology, as opposed to if you would upload root workspaces to HEP data, and then there's a question, okay, is this still readable in future root versions and stuff like that. Okay, so this is an example of what it looks like. So here, as I said, so you have these different channels, and you can see that you have like different samples in each channel. So this is like a simple signal plus background model. So you can see these two blocks of data where one is named signal, the other is background. You have the yields, and then you have the different kind of systematics. Here I'll not go through this in detail, but this is just to show like the overall structure of the workspace, and kind of that it's kind of captured in this standard JSON format that is pretty ubiquitous, and this will not go away anytime soon. Okay, and then the way that you use these JSON workspaces is that you can pip install pyhf. So this is a kind of like a standard Python package, the same way that you would install NumPy or pandas or something like that. And then you have this command line tool available to you, and you could, for example, just compute like a CLS value based on this JSON file. And so this package kind of comes with a full implementation of the asymptotic formulae, like for the asymptotic version of like all the inference computation. But we also have basically support for throwing toys, and then you can do like a toy-based study if you need to. And of course, once you need to do toys, like all the kind of speed gains that you get from pyhf kind of compound themselves, and it becomes much faster overall. Okay, so here, so we do try to make it easy to compute like the common results. So if you want to do like a Brazil band plot for like your signal strength scan for like upper limits, or you want to do like a pull plot or an impact plot, we try to provide an API that makes it easy to generate those, but we're not trying to be a full framework. And so rather we try to be like a good citizen, and for whoever wants to put together a framework should have like a high quality API to make that work. And so there's an example that I linked below called Cabinet Tree, which is trying to build up a framework on top of pyhf. And so it's kind of the same idea of this division of labor, so that we can kind of neatly separate, what's kind of diagnostics and what's like the core likelihood model. Okay, so this is just a plot to show that basically the results are indistinguishable from those computed with root. So this is of course like a very important point, because we've been doing kind of root-based statistics for a very long time, and we kind of trust its implementation. And so and it's quite kind of radical step to do like a lot of the statistics outside of that after that many years. And so we spend a lot of time kind of doing cross checks and validations against the root code base, which is also nice because you kind of for the first time have like a second implementation of all that stack. And here, like what you can see in this plot is kind of an overlay of the results with computed with root and with pyhf. And so it's hard to make out a difference. So in this red contour line that you see, it's actually two lines overlaid on top of each other. But they match so well that it's kind of hard to distinguish the two. And so that's kind of gives us trust that like we've implemented everything correctly. Okay, so one of the reasons for these speed optimizations is basically that we have written this in kind of optimized tensor operations, and then we use auto differentiation frameworks, and those also kind of allow us to use hardware support. And so I'll just go quickly through these. And so so since HistFactory is kind of like a closed world of likelihood, so we have like a finite set of building blocks, and that means that kind of the complexity of the computations is a little bit smaller than if you would try to re-implement kind of RoofFit in total, right? So RoofFit is a very complicated piece of software, partly because it's trying to model, general likelihoods. And so in HistFactory, we have like this finite set of building blocks, and this allowed us to, very deeply optimize the computation. And so all these computations for vertical morphing and all these stuff are kind of implemented in vectorized code, so that we can make use of like NumPy's like C vectorization and stuff like that. And so you can kind of see that all of the HistFactory likelihood computation is kind of expressible in terms of like order of 100 basic math operations. And the complexity of this graph doesn't really change if you add more samples or more regions. And so this is pretty optimized, and so that's one of the reasons why it's so fast. And then the other thing is that, okay, once we've expressed this as kind of vectorized computations of multidimensional arrays, we can not only use NumPy, which is the default, but we can also use kind of all these other array libraries that have come out of the machine learning community, which are like TensorFlow, PyTorch, and recently JAX. And one thing that these alternative backends give us is that we get cheap access to kind of the gradients of the likelihood. And so if we try to minimize the likelihood, having an exact computation of the gradient is very useful. And the other thing that it gives us is that we can basically get, without doing a lot of work ourselves, we were able to run these fits on GPUs. And so that's obviously nice as well, as the kind of the statistical models become very complicated. And so here there's just a plot kind of comparing the performance. On the right-hand side, you kind of see like the fitting time as you're kind of increasing the model complexity to the right. So on the x-axis, you have the model complexity, and on the y-axis, you have the fitting time. And you see, okay, as the models become more complex, the fitting time increases. But so root is in black, and then you can see that the increase in the fitting time in these kind of in pyhf with these different frameworks is delayed, and so you can fit more complex models much faster than with root. On the left-hand side, you can kind of see a comparison between like running this on the GPU and the CPU, and so you can see as you go to more complicated models where you have more and more kind of Nugent's parameters, there's a big difference between running on CPUs and GPUs, so you get like a factor of 10. And so that's also something that, especially for complicated statistical models, makes a difference. Okay, so I did want to connect this to work that has been done in CMS. So this is quite a similar effort in some ways to what Josh David has been trying to do in Combine for TensorFlow. And so I think, if I recall correctly, this has come from the W helicity measurement. And so I'm linking some slides that he's presented before, and he's done a very kind of detailed performance studies on different GPU types and all that stuff. And so I think it would be quite interesting if we can join efforts and kind of learn from our experience, and maybe we can kind of reuse some of that stuff that we're developing and not reinvent the wheel. So for example, we've done all the like asymptotic implementation, and so we're happy to kind of share that code, and maybe we can kind of develop some common tool set. And so one thing that we're trying to do with pyhf is that we try to provide these machine learning framework backed statistics out of the box. So at pyhf, Josh gave a talk where he was saying, okay, this was done specifically for W helicity measurements, and so it's unclear whether or not it will kind of be merged back into mainline Combine. And so in pyhf, that's exactly what we're trying to do. And yeah, so maybe we can kind of collaborate on that. So the last thing I wanted to talk about is reinterpretation. So since this is the B2G group, reinterpretation, of course, a key aspect of kind of the beyond standard model search strategy at the LHC. And so just to quickly describe this cartoon, so the reinterpretation is basically this idea that you take a fixed analysis, and which is analyzing some fixed signal regions, and you kind of realize that this signal region or this phase space region is kind of not only has a high acceptance to the original model that was designed for, but it also has high acceptance for alternative models which happen to have like a similar final state. And so the idea is that you can just reinterpret or generate new scientific results by keeping the entire analysis fixed, but you only switch out the signal component. So you keep all the data fixed and all the background estimation, which is the bulk of the work, fixed, but you compute kind of the new signal component in that signal region, then you can rerun a statistical analysis. And so one thing we try to do in pyhf is that we try to make it easy to reason about it and easy to perform these types of reinterpreted inference runs. And so one kind of thing that helped me a lot while thinking about it is that you can kind of think of reinterpretation as a patching operation in the same way that you would patch like a piece of source code. And so you could kind of take like the background only model, and so either you remove the signal if necessary from like a signal plus background model, or you just have the background model already and then you add like a new signal, and then you get like a new signal plus background model, and then you run inference and then you get a new limit. And so by basically patching the likelihood by adding this new signal, you get this new reinterpreted result. And so one thing that is nice, like a nice side effect of using JSON as a core data format, that patching JSON documents is something that is done in industry a lot. And so there's like a actual like file system, like a file format that is called JSON patch, which is basically like a analog of like the patching file format that you use in Git or something. And so this makes it easy to kind of remove certain pieces from the likelihood and like replace them with a new piece of the likelihood. And so this is kind of shown in this slide where you have on the left, you have like the base likelihood, and in this in smaller box, you can see like a JSON file which has like all the patching operations. So it's basically replacing like the data yields in some kind of signal component, and then through that you get like this new likelihood, and then you can just recompute like a CLS value. So basically reinterpreting becomes the art of generating these new patch files. And so that's of course where the hard work is kind of hidden. And so this is kind of linked nicely with likelihood preservation. So the idea that we had here is that we basically upload to HEP data the base likelihood, which has no signals, like the background only model. and the original signal grid. So this is kind of like a set of these patches for each of the signals that were considered in the original analysis, and then reinterpreters either outside or inside of the collaboration can generate new patches and combine them with this published likelihood, and they will basically get like a state-of-the-art background estimation with all kinds of systematic uncertainties and all that stuff. And so we've seen kind of the phenomenology community pick this up quite nicely. And okay, so this basically brings me to my summary. So basically in Atlas, we've developed like a pure Python implementation of our main bin likelihood model, which is HistFactory. And it's very fast, it's easy to use, and kind of native to Python, and uses newer techniques like auto differentiation, which help make these fits so fast. It also kind of somewhat accidentally helped us achieve full likelihood preservation, which has been kind of priority for us for a long time, and we've seen like a speedy pickup from the external Pheno community, and I think it would be really nice to explore how we can join forces with CMS or like a combined development team. So maybe we can extend the JSON schema to fit also combine, or we can write a combine to HistFactory translator. And so I think there are many options, and would be interesting to discuss. Okay, thank you.
Thanks, Lukas. That was great. So I'm sure that there probably are questions from the audience. At least I have a bunch of questions, but let's see if other people have. So if not, if not, I can then start, and then we can probably other can jump in later. So I must say that this JSON patch is really sort of both very cute and it's a killer app in the sense that this is something that sort of is very cool and may make things sort of quite a bit easier to sort of edit these files on the fly. I have a couple of sort of questions. I think mostly, I think having combined to pyhf translator of some kind, I think probably should not be a huge problem. Combine is actually also in mostly in Python, and I think it just makes these there are sort of there's code that makes these text files that config files for combined cards, and I think that the information content is similar to JSON files. So I think that's all, which kind of makes sense because the fit that's driven by physics. So I think that's sort of one way to think about this. I have sort of a more kind of prosaic and question of so people use root, and so one question is that how do you actually load histograms? I mean, so we run some root code or something, and it produces bin histograms.
Yeah.
And then how do you actually, is there some way to kind of translate them into format that you want? To some,
yeah, so I don't have like the right backup slide for that, but yeah, we have like kind of like an automatic translator. So if you kind of have like a standard HistFactory setup where you have like all these XML files and root files, we can basically, so in the pyhf command line interface, you can say pyhf XML to JSON, and it will do this conversion from the left-hand side to the right-hand side automatically from you, and it will use uproot to read the root files and then read out all the histograms and convert them into this JSON format. And so that, and it works in both directions. So we can also convert back to the XML plus root version, which might be interesting once you want to do like combinations with larger groups of analyses. And yeah, so that's there. And yeah, so you could basically kind of try to find also like a conversion from like a combined data card to this JSON format. And one thing that we've kind of learned when we developed PyHF in the first place, it's not needed to have like a fully featured set up in the beginning. So we started out with like one type of systematics, which is like just scaling like the background with some standard scale factor. And then as we kind of go on, we added all the remaining ones. And so maybe starting with a very simple combine example would be like a good entry point.
Yeah, I think I was at I mean, that's why I was asking, is because people will say, okay, I have histograms, you know, I want to set up something that, you know, use PyHF. It's a, you know, 3-component fit. I have, you know, templates for these. I want to use them. You know, people generally know exactly what they need to do. And then once they figure out how to do one thing in PyHF, they can do immediately 10. So I think this is sort of
Right.
one of these cases, like where the kind of the first entry level step is like, well, how do I load my histograms into, you know, a PyHF? Which also kind of makes it nice because people want to make, people are used to using root in making pretty, you know, publication level, you know, quality plots. They may not know how to use, you know, whatever matplotlib from Python. Certainly I don't. And, but, you know, so making these plots and making the post-it plots, I think with root, or prettifying them with root, I think would be very useful. So once if you can get hold of, you know, information from PyHF.
Yeah.
Okay, excellent.
Yeah, so
So
one thing
also-
that we're trying to do generally in PyHF is we do try to maintain this bi-directionality so that you can also go back to root for some part of the analysis. And one way that we try to do this is, for example, like in this example where you compute the CLS value, like all the outputs are like JSON files, and then you can read them back in C++ if you want to. And then you can do like, so once you've kind of computed all your CLS results and you want to do like a contour plot with root again, you can just write this out to like flat text files and then do your computation in root.
Okay, I think Matthew wanted to add something.
Oh yeah, sorry. I was just gonna point out that both Jordan and Alex have been dropping some links in the chat. If people will, just to make sure that people saw them, that have kind of address some of these points. So, for example, Jordan has pointed once again to Alex's cabinetry, which as well as kind of to the PyHF docs itself, just to kind of highlight some of the kind of different recipes or different ways that we already have. If you have root files to be able to get them out. And then Alex has also pointed out that you can, of course, given that at the end of the day, we're just getting, you know, we're translating histogram objects into just arrays, that you can also just use uproot, of course. This might also be, and as Alex is, in addition to his own work, is also pointing to the actually very nice work from a CMS member of MPL-HEP, which is a scikit-HEP project. This might be a good time to point out as well that that PyHF itself is also a scikit-HEP project and is so openly developed on GitHub. And so it's not an Atlas internal project, but it's a open community project. Likewise, Alex's cabinetry is openly developed on GitHub as well as part of an effort from IRIS-HEP.
Okay, great. Can I ask a question? I'll actually turn on my camera so it's not anonymous across the ring. So I saw that your setup instructions are mostly, I mean, I think they're entirely based on Python 3, which, you know, there's good reason for that. However, CMSSW is still on Python 2 while we're migrating to Python 3. So I was wondering if there was an easy way just to, say, get started on LX Plus, either with Python 2 or Python 3, and if these instructions can be found somewhere.
Yeah, so the good news is, okay, so yeah, PyHF is Python 3 because we want to make sure that we take advantage of all the nice work done by these backends, which are also all Python 3. So I guess I'll kind of plug this, that this week, actually this Friday, Jordan is going to be giving a tutorial at an Atlas workshop all about basically the how to get started with PyHF. But he's in that tutorial, which I think we can actually make everything public on. There's instructions that actually show you exact setup commands if you're on LX Plus or Atlas Connect or something like that. Just anything that has CVMFS on how to get a Python 3 environment that you can then trivially set up a virtual environment, install Python in, or install pip in, or sorry, install PyHF in.
Yeah,
Okay.
so kind of fallback solution, we also kind of have Docker image, which are also usable using singularities. So if you just want to run like a simple script, you can just drop into this container and then, yeah.
Okay, great. And another question on slide 15. I think I mean you were referring to cabinetry, but in particular you had to say some of these standard statistical test plots, so the poles here on the right hand side. And I was wondering, since you were pointing out that this is like a building block, does one need cabinetry in order to make these plots, or is this something that can be done within PyHF? So, for instance,
so we have example notebooks that allow you to kind of create these standard plots, and so, but we're not kind of making any claim in terms of completeness. So these three particular plots we knew people wanted to make, and so we kind of invested some time to make that work. But yeah, if you want to kind of do something beyond that, you might want to code this up yourself. And usually that's not too hard to do. So these notebooks for the pole plots are kind of straightforward, but yeah, if you're kind of looking for like a managed or a solution where this is being done for you, then it's more kind of towards cabinetry. I'm not sure if Alex wants to comment.
So maybe I can mention on cabinetry, this is Jordan. So one of the things is that when you're doing these sort of statistical fits or sort of statistical tests, such as parameter scans or impact plots or profile, these are things where you effectively take the likelihood and you scan or you do a bunch of different configurations and compute something. Where you want to do something like, say, go from n tuples to histograms, and then build pre-fit or post-fit distributions, that's where you would want cabinetry to come into play. So cabinetry builds on top of PyHF by relying on PyHF to do all the statistical fits, but cabinetry will make it a little bit easier to build these sort of per sample distribution before and after a fit.
Hi, this is Alex. Just to add something, I mean, of course, these like plots that show up here, they're not very complicated operations. So like you can easily code them up yourself and visualize them yourself in any way you want. The one thing in cabinetry that it does, it has implementations for them. That's so that instead of having to write your own script, you call the function and then you get the plot out of it with a bit of cosmetics applied so that it scales to the amount of parameters and these sort of things. But for sure, I mean, these things, if you want to calculate stuff in another way or so, it's not a lot of work to re-implement them yourself as well, but not everyone may want to write their own implementations, but instead use something that's centrally provided.
Okay, thanks.
This is Kyle. Can I make a quick comment on this? In the efforts that I have from on IRIS-HEP, which is sort of like similar to HSF, and trying to organize some of these. One thing that we were trying to do around this topic in particular was to try to establish some sort of language and some specifications for these different types of plots, because my feeling is that a lot of these plots developed kind of organically within the experiments, within the review process. Like, what kinds of things do people want to see to be convinced that everything's fine? And there's a lot of jargon involved in terms of like what you call them and how people interpret them and how people assume that they're made. And so one thing that Alex was working on doing was trying to define kind of specifications for these different types of plots to define exactly like what they mean, and then once we have those, then we could imagine writing, potentially multiple different implementations Some could even be in root, some could be in Python or whatever, but that kind of quest of sort of establishing some specifications for these plots, I think, is useful. And it's a place where like having Atlas and CMS maybe have some sort of meeting where or some process where we could try to like kind of agree on what we want to call these things and agree on the semantics of them, I think would be pretty useful.
Okay, great. Okay. Well, I think we have time for maybe one more question, and then I guess we need to move on with our meeting. Are there any other questions?
So this is better. I do have one question, which is maybe important, which is you mentioned vertical template morphing. Do you have other kinds of template morphing? Because that, in a sense, I think, so clearly vertical template morphing is good enough for most cases, but I think it would be interesting to, at least I'm curious to know whether other options are available.
Maybe I could handle that one. So there's lots of things that you could do, and there's like extensions of HistFactory that people have done, or things that are not quite part of the HistFactory specification that allow for horizontal morphing. But the sort of version 1 HistFactory specification, which has been used, that's part of root and XML and been used for a long time, does not have horizontal stuff. You can try to kind of create that through some other means, but we're now talking about kind of extending the specification to include that kind of stuff. But that would be sort of like a version 2 of the HistFactory specification.
But it's something that, is it something that I can plug in? And I mean, for instance, how easy would it be for me to plug in, hypothetically, for me to plug in new, horizontal template morphing if I really wanted to do this?
Yeah, so in terms of PyHF, so all of these different parameterizations are kind of implemented using a standard API. And so if you want to kind of add your new type of parameterization, you could kind of develop a new one that kind of satisfies the same API and plug that into PyHF. But if you but that would be kind of like an ad hoc extension of PyHF, and I think kind of collecting like a new set of basic building blocks, like Kyle said, would be kind of useful long term. But yeah, so like the way that it's implemented in
specification is kind of, the code can do it, it's the specification doesn't have it. Yeah.
Okay, thanks. So I don't have any other questions other than I'm itching to, try this. I actually installed the PyHF, on my laptop, but now I have a new desktop, which actually has a powerful GPU card on which I can actually run this, and it may be useful. So I really want to try that.
Okay, yeah, great. So maybe the last thing I wanted to add is just, if anybody from CMS wants to try this out, or maybe wants to work with us to try to see whether or not we can take like a simple combined example and translate that to PyHF, I think we'd be very happy to kind of work with you.
I think the biggest problem that we have is that our examples are